Welcome to Philosophy Unplugged, the show where we explore the profound questions that shape our understanding of reality. Today, we're diving into the fascinating journey of the philosophy of space and time, from Newton's classical mechanics to Einstein's groundbreaking theories of relativity. The concepts of space and time have always intrigued philosophers, scientists, and thinkers throughout history. From the ancient Greeks to modern-day physicists, the nature of space and time has been a central topic of inquiry, shaping our understanding of the universe. The evolution of these concepts from Newtonian mechanics to Einstein's theory of relativity marks a significant paradigm shift in the philosophy of space and time. This article explores this transformation, delving into the contributions of key figures and the philosophical implications of their theories. Newtonian mechanics, absolute space and time. Sir Isaac Newton's work in the 17th century laid the foundation for classical mechanics. His Principia Mathematica, published in 1687, introduced the concepts of absolute space and absolute time. According to Newton, space and time exist independently of any objects or events within them. This view can be summarized in two key points. 1. Absolute space. Newton postulated that space is an infinite, immovable, and immutable container in which all physical phenomena occur. It exists independently of the objects within it and provides a reference framework for measuring positions and motions. 2. Absolute time. Time, in Newton's view, flows uniformly without any reference to the events occurring within it. It is a continuous, unidirectional progression that is the same everywhere in the universe. Newton's absolute space and time provided a clear and straightforward framework for understanding motion and dynamics. His laws of motion and universal gravitation described how objects interact within this fixed stage. While these ideas were immensely successful in explaining the motions of planets and objects on Earth, they left several philosophical questions unresolved. For instance, if space and time are absolute, how can we detect their true nature if we are always within them? Leibniz's relational space and time. Contemporaneously with Newton, the German philosopher and mathematician Gottfried Wilhelm Leibniz offered a different perspective on space and time. Leibniz argued for a relational theory, in which space and time are not entities in themselves but rather systems of relations among objects and events. 1. Relational space. According to Leibniz, space is a network of spatial relationships between objects. It has no existence independent of the objects it contains. The distance between two objects, for example, is defined by their relative positions rather than their positions within an absolute framework. 2. Relational time. Similarly, Leibniz viewed time as a sequence of events. Time does not exist independently but is a measure of the progression of events. The interval between two events is defined by the sequence of occurrences, not by an external temporal backdrop. Leibniz's relational view emphasized the interconnectedness of objects and events, rejecting the idea of an empty, unchanging stage. This perspective influenced later philosophical debates about the nature of space and time, challenging the Newtonian framework. Kant's synthesis, space and time as forms of intuition. In the late 18th century, Immanuel Kant provided a synthesis that sought to bridge the gap between Newton's absolute concepts and Leibniz's relational theory. In his Critique of Pure Reason, 1781, Kant argued that space and time are not inherent properties of the external world but rather forms of intuition through which we perceive phenomena. Forms of intuition. Kant proposed that space and time are a priori conditions of human perception. They are the fundamental frameworks within which we organize sensory experiences. According to Kant, we cannot perceive objects or events except within the constructs of space and time. Transcendental idealism. Kant's transcendental idealism posited that while space and time structure our experience of the world, they do not necessarily reflect the world as it exists independently of our perception. This view implies a distinction between the phenomenal world, as we experience it, and the noumenal world, as it exists in itself. Kant's ideas significantly influenced the subsequent philosophical discourse, emphasizing the role of the observer in shaping the experience of space and time. The shift to modern physics, the birth of relativity. The early 20th century witnessed a revolutionary shift in the understanding of space and time, driven by the advent of Albert Einstein's theories of relativity. Einstein's work fundamentally altered the philosophical and scientific landscape, challenging and ultimately superseding Newtonian mechanics. Special relativity, 1905. In his theory of special relativity, Einstein proposed that the laws of physics are the same for all observers in uniform motion, regardless of their relative velocities. This theory introduced the concept of space-time, merging the three dimensions of space with the dimension of time into a single four-dimensional continuum. Key aspects of special relativity include: 1. Relativity of simultaneity. Events that are simultaneous in one frame of reference may not be simultaneous in another. 2. Time dilation. Moving clocks run slower relative to stationary ones. 3. Length contraction. Objects in motion contract along the direction of motion as perceived by a stationary observer. General relativity, 1915. Building on his earlier work, Einstein developed the theory of general relativity, which describes gravity not as a force but as a curvature of spacetime caused by mass and energy. Key components of general relativity include 1. Spacetime curvature. Massive objects cause a curvature in the spacetime fabric, influencing the motion of other objects. 2. Geodesics. Objects move along geodesics, which are the straightest possible paths in curved spacetime. 3. Gravitational time dilation. Time runs slower in stronger gravitational fields. Einstein's theories had profound philosophical implications. They challenged the Newtonian notion of absolute space and time, demonstrating that measurements of space and time are relative to the observer's state of motion and the presence of gravitational fields. This shift from absolute to relative concepts of space and time marked a significant departure from classical mechanics. Philosophical implications of relativity. Einstein's theories of relativity not only transformed physics but also sparked extensive philosophical discussions about the nature of reality, the role of the observer, and the structure of the universe. Relativity and reality. The relativistic view suggests that space and time are not fixed entities but dynamic and interdependent. This has led to debates about the nature of reality itself. 1. If space and time are relative, what does this mean for our understanding of the universe? Is there an objective reality, or is reality shaped by the observers within it? 2. Role of the observer. Relativity underscores the importance of the observer in the measurement of space and time. This aligns with philosophical ideas that emphasize the subjective nature of experience, echoing Kant's notion that our perception of space and time is shaped by our cognitive faculties. Space-time and causality. The concept of spacetime intertwines space and time into a single continuum, affecting our understanding of causality. Events that are causally connected are now seen as part of the fabric of spacetime, leading to new ways of thinking about cause and effect. Determinism and free will. The deterministic nature of classical mechanics, where future states of a system are precisely determined by its initial conditions, is challenged by relativity. The probabilistic interpretations in quantum mechanics, which emerged around the same time as relativity, further complicate the picture, raising questions about determinism and free will. Concept of time. Relativity introduces the idea of time as a dimension similar to space, leading to the block universe theory, where past, present, and future coexist in a four-dimensional structure. This challenges the common-sense notion of a flowing time and has implications for our understanding of temporal experience. Conclusion. From Newton to Einstein and beyond. The journey from Newtonian mechanics to Einstein's theory of relativity represents a profound evolution in our understanding of space and time. Newton's absolute concepts provided a clear and effective framework for classical mechanics but were ultimately limited by their inability to account for the relative nature of measurements observed in high velocity and strong gravitational contexts. Einstein's theories revolutionized this framework, demonstrating that space and time are not absolute entities but are intertwined and relative to the observer. This shift has not only advanced the field of physics but also provoked deep philosophical inquiries into the nature of reality, the role of the observer, and the structure of the universe. As we continue to explore the frontiers of physics with theories like quantum mechanics and string theory, our understanding of space and time will undoubtedly evolve further. The philosophical implications of these advancements will continue to challenge our perceptions and expand our knowledge of the cosmos. The dialogue between philosophy and physics remains crucial in this ongoing journey, driving us to reconsider and refine our concepts of space and time in the ever-unfolding tapestry of the universe. Thank you for joining us on this exploration of the philosophy of space and time. This has been Philosophy Unplugged. Stay curious, and until next time, keep questioning the nature of reality. If you enjoyed this episode, don't forget to subscribe and leave us a comment. Until next time, stay philosophical.